Hello everyone, welcome to this lecture of the course Digital Electronics and Circuits, and in this particular lecture we will be talking about two more combinational circuits, and these are decoders and encoders. Right, to begin with, let's understand what is a decoder. Right, when I say when we say decoder, we either say it's like a N to 2N decoder. Basically, this would mean when we say a decoder, it will be 2 is to 4 decoder, or 3 is to 8 decoder, or 4 is to 16 decoder, so on and so forth, right? So n is to 2n decoder uses its n bit input to determine which of the 2n outputs will be uniquely activated, right? So if I say we have a combinational circuit over here, right, and we have a 2 is to 4 decoder where we have two inputs and we have four outputs, correct? And let's name this input as S1 and S0 and outputs at Q0, Q1, Q2 and Q3, right? So basically this 2 is to 4 decoder uses its 2-bit input to determine which of the four outputs is uniquely activated, right? So basically if we have to put this in terms of truth table, if I say if I have S1 and S0, so what all the possible combinations of inputs are there? 0 0 0 1 1 0 1 1. What will be the possible combinations of output in such a case? So basically it tells only one of the output has to be uniquely activated. If 0 0 is the case, Q0 will be activated. If 0 1 is the case, Q1 is activated, right? If 2 is the one, Q2 will be activated. 3 is the one activated. So basically depending upon the select lines, right, we can simply say these are select lines, and depending upon the select, like one of these clients would be active, right? Sort of an arbitration logic, right? When depending upon whatever the inputs are, one of them would be active at a time, right? So basically if at all we have to draw a block diagram, right? So how do we draw a block diagram for this particular thing? We can simply, based upon this truth table, we can say Q3 is nothing but S1 S0. So basically for each and every output only one term is true, right? Q2 will be equal to S1 S0 bar, Q1 is equal to S1 bar dot S0, and Q0 is equal to S1 bar dot S0 bar, correct? So basically this particular circuits decode a binary number out in 1 out of 4. This we have already seen. Now we have already seen what will be the expressions of Q1, Q0, Q2 and Q3. And if we have to draw a circuit diagram for this, right? Let's assume we have two lines, S1 and S0 as a select lines, right? And let's assume we have a knot of this line going parallel. Similarly for S0, let's assume we have a knot line going in parallel. Now what we can do is we can simply say Q3 is nothing but this S1 and S0. Similarly Q2 is nothing but S1 into S0 bar. So on and so forth. So basically this decoder circuit would be implemented via we would have like two NOT gates and four AND gates, correct? So this is an example of a decoder, a simple decoder with two inputs and four outputs, right? So what we can do is like we can have various variations of these decoders, basically the arbitration circuits, where we can say let's have a decoder with an enable switch, where we say that okay, if we have a decoder block over here, we have two inputs S0 S1 and outputs Q0 Q1 Q2 Q3, but let's have an enable input. Basically what does this mean is whenever enable is equal to 0, right, it means that a decoder is disabled by default. Basically decoder is not in use. When enable is 1, right, it's the same decoder as specified earlier as we saw just now, same as the one we discussed. So how does the truth table for this one looks, right? So we have three set of inputs, one being enable, one being S1, one being S0, right? So basically, and we have a multiple set of output. So basically, if my enable is 0, I don't care what S1 is, I don't care what S0 is, output has to be all zeros. Similarly, one enable is 1, right? We have multiple cases where dependent upon S1 and S0, whether it's 0, 0, 0, 1, 1, 0 or 1, 1, we either have this working or this operational or this operational or this operational, right? This is an decoder with an enable input. Basically, where we say that, okay, my decoder might not be active at all the times, we have an enable pin. We have already looked at, like, this is like an example of 2 is to 4 decoder. Now let's look at a 3 is to 8 decoder. A 3 is to 8 decoder would be something like, right, we have set of 3 input lines, which are like 3 select lines, S2, S1, S0, and we have set of 8 outputs from Q0 to Q7, and then we have an enable bit. Now, basically the thing is, right, how do we write a truth table for 3 is to 8 decoder? We will have something like S2, S1, S0, and then we have enable as well. Similarly, we have set of outputs from so on up to Q7, right? If enable is 0, irrespective of what these are, everything will be 0. Now, if enable is 1, depending upon the combination 0, 0, 0, 0, 0, 1, 0, 1, 0, so on and so forth till 1, 1, 1, right? We can either have Q1 active or Q0 active, or we can have Q1 active, or we can have Q2 active, and finally we can have something like Q0, Q7 active, right? This is a 3 is to 8 decoder, and if you see, if you have to build this 3 is to 8 decoder, what we have to do is we have to take enable into consideration, and then what we can do is then looking at each and every combination, right? Q0 would be equal to enable dot S2 1 bar S0 bar, right? And similarly, right, each of the expression of this decoder with one term would be activated. Q0 would be activated for one set of a term, Q1 would be activated for another set of term, and Q3 will be activated for another set of term. Now, for example, right, this is Q0, Q1 will be enable is common being ended, S2 bar, S1 bar, S0. Similarly, Q7 is nothing but enable S2, S1, S0. So basically, if we look at this, right, if we assume that enable is a common constant in all the terms, because that is what we have, whether if depending upon enable, whether everything output is 0 or one of them would be active, we would see one important use of the decoder. Decoder is nothing but a minterm generator. We have already seen minterms and sum of product, right? So if you see, since each of the output of decoder is true for exactly one of the inputs, minterm generator can be realized using a decoder circuit. Same is true for 2 is to 4 decoder also, where we saw Q3 is equal to S1 S2. So basically this is same as saying I have something like XY X bar by XY bar X bar by bar, correct? So this is the same thing. So this is a minterm generator, and this minterm generator circuit could be used in realizing multiple circuits. Now, having said this, right, we have a problem statement. So we looked at 3 is to 8 decoder, and we looked at 2 is to 4 decoder. Let's assume I have two 2 is to 4 decoders, and I have to build one 3 is to 8 decoder. Can we do that? Yes, this is possible, and for doing this, right, we have to look at the truth table of 3 to 8 decoder again. Let me quickly draw it. So these are the possible set of inputs, and depending upon these inputs, one of the outputs would exactly be active at a given point of time, right? So if it is 0, this will be active, then this one, fourth, fifth, sixth, and seventh. And now what you see is, what we can do over here is, if you see over here, we have S2 being 0 in half of the entries and S2 being 1 in half of the entries. And our problem statement is, we have two is to 4 decoders. So basically internally this is S0, this is S1, and this is internally 4 outputs. And then internally we have 4 outputs. This is 2 is to 4 decoder, this is 2 is to 4 decoder, this is again S1, this is again S0, right? Correct. And basically you can just nomenclature wise, these are all Q3 to Q0, this is again Q3 to Q0, and then we have an enable pin as well, which we know that how it works, right? So now what I can do over here is, and the function of enable pin is, when enable is equal to 0, all outputs 7 down to 0 are 0. When enable is equal to 1, the output 7 0 down to 0 follow this truth table, correct? Now in this case, as I say, right, S2 being 0, what I can do, S2 being 0, I care only about these 4 outputs. S2 being 1, I care about only these 4 outputs. So what I can do is, if I directly connect S2 to this enable, basically when S2 is 0, enable is 0, this particular set of decoder would be disabled. And what I can do over here is, we can simply put a NOT gate and connect this S2 to this particular enable. If S2 is 0, the upper decoder is disabled. If S2 is 0, this particular decoder is enabled. And now depending upon what are the values of S0 and S1, one of the outputs would be selected, right? Similarly, we can connect S0 and S1 here also. When S2 is 1, uh, this would be disabled, this would be enabled, and basically we will get output of Q7, Q6, Q5 and Q4 over here. So this is one of the important usages of that enable switch also, that we were able to construct a 3 by 8 decoder using two by 4 decoders, right? And we already spoke about a function of this decoder being in the arbitration logic, because one line would be active at one point of time, and then we also saw that this could be used as a min term generator. And see, basically we told that, okay, this could be used as a min-term generator. Can we see an example of this, that where it can be used as a min-term generator, right? We have already discussed about full adder, right? Which is nothing but 3-bit adder. Let's assume our 3 bits are X, Y, and Z, right? And we already saw, like, uh, carry was X uh, or Y into Z. Sum was X XOR Y XOR Z. Basically, when we looked at previous lecture, if you look at it, right, this would come like summation of 1, 2, 4 and 7, and this was summation of M, 3, 5, 6 and 7, right? Basically this adder circuit, right, this full adder circuit we can implement using a decoder. And how do we do that? Let's assume that we have a 3:8 decoder over here. We have S2, S1, S0, then we have an enable signal, and then we have output, right? 07, 06, 05, 04, 03, 02, 01 and 00, correct? Now what we can do simply over here is, we can supply 5 volt or logic level 1 over here, right? And then what we can do is S0, S1 and S2 can act as XYZ, and then all the outputs, right, 1, 2, 4 and 7. We can tap this output. We can OR them together, and this will give us sum. So basically, if we have a decoder available, we can just add a OR gate, and basically we can get a sum term. Similarly, we can OR these terms 6, 7, 5 and 3, and we can have a carry operation with us, right? And basically, if you look at it, right, if you have to verify this particular thing, what would be my O0 would be? O0 would be X bar, Y bar, Z bar. Enable is 1, so this dot is 1. My O bar would be 1. It would be 1, right? So X bar, Y bar, Z, and so on and so forth, right? So basically, we were able to use this decoder as a min-term generator and implement a adder circuit by only using a OR gate. Now, whatever we looked at till now, right? We started with the 2:4 decoder. We said we had S1, S0, then we had an enable, and then we had four outputs, Q3, Q0. Now, basically, what is happening over here is all the pins are active high, right? So basically, we can have a variation in a decoder where what we can say is instead of active high signals, we have active low signals. So let's assume my signals are something like this is enable. So here I can input enable bar. So basically I can ground this pin, right? We can ground this to make it active, and basically output would be Q3 bar, Q2 bar, Q1 bar and Q0 bar. Correct? In such a table, this is known as active low decoder. And if you have to draw a truth table for this, right? So enable bar, if enable bar is 0, only then it is active. And if enable bar is 1, I don't care about S1 and S0 are output, right? Q0 bar, Q1 bar, Q2 bar and Q3 bar would be all 1 because this is active low decoder. Output means being 1 means these are not active. And similarly, if enable bar is 0, then is when the enable is functional, this encoder is functional, decoder is functional, and depending upon the values of S1 and S0, what we can simply say is when it's 0, right, only one of them would be active. So basically for 0 0, my Q0 would be active and the output of Q0 bar would be 0. It's active low. This will be like this. It will be like this 0, and all being 1 means Q3 is active low. So basically this will be like, right. Now here what we can say simply, here we can simply say that Q0 bar, which is 0 over here, right? So Q0 bar is nothing but this is equal to S1 bar plus S0 bar, right? Or basically I can say that since Q0 is equal to S1 bar dot S0 bar, right? So basically what we were looking is we were looking for one active number, and Q1 bar is something which is the output, and the output if we have to explain right in terms of input Q0 bar whole bar. This implies Q0 is equal to S1 bar dot S0 bar, right? Because this is Q1 bar and for it to be 1 it has to be not of that. So if we do a bar over here, right, we will simply say that my Q0 bar is S1 bar dot S0 bar. Similarly, what would happen is I would get other expressions. For Q0 Q1 bar, my Q1 bar would be equal to S1 plus S0 bar. Q2 bar would be equal to S1 bar plus S0, and Q3 bar would be equal to correct. So is this clear? How did we arrive at these equations? And depending upon this equation, right, if you see over here, this particular active load decoder is acting like a max term generator. Correct. We had a situation where we had an active high decoder where which we saw was used as a min term generator, and we saw an example also where we implemented a adder circuit using a decoder. Correct. Now what we did is we did a variation in this circuit. We said okay, let's have active low enable and active low outputs, and depending upon these outputs, right, what we did was we draw the circuit diagram, and depending upon the circuit diagram we drew a truth table where we said q0 bar is equal to s1 plus s0. All right. Okay, so basically there is a mistake over here. So as I said over here, right, q1 bar is 0, so q1 bar is s1 bar dot s0 bar. So q0 is this much, and if I assume that q0 bar would be equal to de Morgan's law, it will be s1 plus s0. So basically, if you see, right, this is reversed. So this is not 3, this is Q0, this is Q1, this is Q2, and this is Q3. The other way of driving this would be, if we look at Q3, right? So if we look at over here, Q3 bar is 0 over here. So if I say Q3 bar whole bar 1 is equal to S0 dot S1. This would implies Q3 is equal to S0 into S1. This would imply Q3 bar is nothing but not of this S0 bar plus S1 bar. So these are the correct expressions, and we already saw a max term generator where a decoder could be used as a max term generator, the active load decoder. Right. So this was all about decoders, where we spoke about like what is a decoder circuit, and is to 2 and decoder. Then we saw an example of 2 is to 4, 4 is to 8, and then we looked at how the decoder is used as a min-term generator. We did a variation to the decoder where we added an enable signal. When enable is 0, all the outputs are 0. We spoke about a 3 is to 8 decoder, and then we constructed a 3 is to 8 decoder using 2 is to 4 decoders using a select line and enable with one extra NOT gate. And eventually we saw an example of decoder being a min-term generator using a after implementing a full adder. Then we saw one more variation in the decoder circuit where we had like active load decoder, and that active load decoder we saw was nothing but a max term generator. This was all about decoders. Now let us talk about encoders, right? So encoder is nothing but it's like a inverse of decoder. Like we have n is to 2 n decoder. Encoder is nothing but 2 raised to power n to n. So basically encoder is a digital circuit that performs inverse operation of a decoder. An encoder has 2 raised to power n input lines and n output lines. So the block diagram of encoder would be something like, so basically this is like 4 is to 2 encoder, Q0, Q1, Q2, Q3, and then we have two outputs, O1, O0, right? And the thing is, right, we have only eventually, like if an encoder is there, at least exactly one of them would be active, and depending upon which one is active, uh, the output logic will be displayed over here, right? The output line generates the binary equivalent of the line whose value is 1. Correct? Is this fine? Let's look at an example for an encoder, right? So basically this is 4 is to 2. Similarly there will be 8 is to 3 encoder as well. Correct? So when we talk about 8 is to 3 encoder, what we would say is like we have 8 inputs. Let's call them D7, D6, D5, D4, D3, D2, D1, D0, and then we have outputs, right? Outputs would be 3 outputs, A2, A1, A0. Let's call them like this. So well, if my d1 is 0, depending upon like all of them are 0, if one of the active outputs is 1, right? In such a case, what would happen is my output will be reflecting a value 0. So this will be 0, this will be reflecting a value 1, right? Similarly, we will have a value 2, value 3, value 4, like this, right? 2, 3, 4, and 5, 6, and 7, rest all being zeros. So basically we have 5, 6, and 7, right? In this case, it simply means my A0 is nothing but combination of D1 plus D3 plus D5 plus D7. Similarly, my A1 01 is D2 plus D3, so on and so forth, right? So this is an encoder example, but there are two problems in this encoder example, right? So there are two problems in the sense like, what if I have more than one input? My input is wrong and I have like set of 8 inputs, and say by default, by definition, we say only one of the inputs would be 1. What if more than one inputs is 1, right? Let's assume, what if I have both D2 and D6 as 1. If both D2 and D6 is 1, right, my output will become equal to what? If D2 is 1 and D6 is 1, my output would be 1, 1. So D2 and D6 will not be a problem because both of them are in the 2 and 6 line frame. But let's assume that my D3 and D6 is problem. D3 and D6 is 1. If D3 and D6 is 1, what would happen is my uh, output would be what? 1, 1, 1, because my d2 will be 1, d6, d3 is 1, d6 is 1. So basically, if you see, d3 would be ensuring that my all the 3 bits become 1. My output will become 1, 1, and 1. So that's definitely a problem if there are like multiple input bits are 1, right? So basically, what would happen as a result, all this a2 a0 will become a1 will become 1, and similarly my a2 will also become 1 because it also depends upon d6, correct? And the second problem is, what if as of today, when my d0 is 1, my a0 is 0, a1 is 0, a2 is 0. What if all the inputs are 0? Still, in that case also, my entire output will be 0 in case of all inputs being equal to 0. So there are two problems in this basic decoder where we looked at like 4 is to 2 and 8 is to 3 decoder, right? So to resolve this issue, we have something called as priority encoders, and this encoder says that if there are multiple asserted input value, right, the one with the higher number takes precedence. And to solve the second problem, right, this is like solving the first problem. What if we have more than one inputs active? We say let's have a priority encoder where once we say that if a higher number is 1, the lower number doesn't vary. And then the second problem is, what if all the inputs are 0? What we do is, in that case, we create a valid signal whether that particular input is valid or not. In such a case, right, how will our truth table look like for my 4 is to 2 priority encoder? For 4 is to 2 priority encoder, right, let's assume we have set of inputs as D3, D2, D1, and D0. And my outputs in this case would be what? I have A1, A0 as output, and let's consume a valid signal. Now, in case all these three are 0, right, what would happen is my A1 and A0 does not matter because my valid becomes 0. Correct. Now comes the second case when my d0 is 1, right, valid is 1, my output has to be 0, 0. Now in case my d1 is 1, I don't care about what d0 is. If higher number is 1, it's a priority encoder, we don't care what lower number has. This will become 0, 1 with a 1. Similarly, once we have d2 as 1, these two are don't care. This will become 1, 0 with a valid 1. If d3 is 1, we don't care what is present over here. What we simply say, this is 1, 1 with a 1. Right? And now if we create a k-map out of this, right, if we try to create a k-map for, let's assume, one of the outputs, let's assume we create a k-map for a1, right? KMF for A1 would be something similar to this. So correct, 0 0 0 1 1 1 0 0 0 0 1 1 1 0, correct. So my A1 would is X when all of them are 0. This is don't care. And then whenever my 1 would come only for a cases where D2 is like number 4 and above, right? So 0 1 2 3 for 4 and above everything is 1. 4 5 6 7 8 9 10 11 12 13 14 15. So this is equation of my priority encoder, and if we do a K map, this will be the two terms, which means my A1 would become equal to D2 plus D3, D2 plus D3. Similarly, if I look at A0, right, A0 would be something like A0 is for 0 it's like X, we don't care about this, and then for any it's 1 for any number like 2 and 3, 0 1 2 and 2 and 3 it's 1, then again it's 1 for any number greater than 8, 8 9 10 11 12 13 14 15. So what are the two numbers? Like this is 1, right, and this one is another pairing for us. So the output over here would be my A1 would be equal to D3, this will be D3, and the last one would be this thing is not changing, this is like D1, and this is like D2 bar, D1 into D2 bar, correct. This is a priority encoder. Similarly, we can have 8 is to 3 priority encoders depending upon what are the don't care situation, right? We have looked at all these things, and before ending this lecture, right, let's talk about what is the use of a priority encoder, right? For priority encoder, what we can use is, let's assume that we have an encoder sitting over here, right? 4 is to 2 encoder. We have 4 set of inputs. We have 2 set of output, right? Encoder. What we can see is we can connect different devices over here. Let's assume we connect a device A, device B, device C, device D. Now, depending upon the priority of the device, right? So basically, if I put 0, 1, 2, 3. So in that case, what would happen is this would be become the highest priority. This would be lowest priority, right? What we can do is all this depending upon the priority of the device, the request of these devices could be served from the, let's assume these two lines are going on to a processor. So this is one of the uses of a priority encoder, right? Where what we can do is we can different devices can request access to processor depending upon the priority order. So this is all about this particular lecture. We talked about two combinational circuits, decoders and encoders. Decoders, we saw min-term generators and max-term generators. We looked at 2 is to 4 decoder, 3 is to 8 decoder, right? And then we looked at how min-term and max-terms are generated. We created a 3 is to 8 decoder using 2 is to 4 decoders. And similarly, then we looked at encoders, and we looked at various variations of encoders and decoders with different valid signals, and priority encoders also we looked at it. Hope you like this lecture. Stay tuned for more.